Okay, I'm working number 13 here from 8.6. So it says use differentiation to find a power series representation for the following. So we cannot get this to look like 1 over 1 minus u because of the squared here. And we can't do partial fractions either. So what we're going to do is we're going to realize that this is actually the derivative of something. So let me start out by trying to show you this. First of all, if I integrate 1 over 1 plus x squared, if I integrate that, make a basic u substitution, u is 1 plus x, du is dx, then this just becomes integral 1 over u squared du. And that's just integral u to the negative 2 du. And if we find this antiderivative, this will be negative u to the negative 1 plus a constant. And that's just negative 1 over u. And remembering that u is 1 plus x, we get this. So, all right, so what is this? What the hell does this mean? This means that f of x, this function, is actually the derivative of this. It's the derivative with respect to x of negative 1 over 1 plus x. So if you take the derivative of this, you get that. We know that because when we integrated that, we got this. So when we do that now, we realize that what's in that parentheses can be written as a power series. So this inside, I'll rewrite that as negative 1 times 1 over 1. So I pulled that negative 1 out. Then I'm going to rewrite this as minus negative x, like that. And now this piece right here is our u, and I'm going to rewrite that using the summation notation. So we get that f of x is the derivative of negative 1 times summation negative x n equals 0 to infinity, negative x to the n. And then derivative with respect to x of, I'm gonna peel that apart. I'm gonna put the negative 1 inside. Take it easy. Sum n equals 0 to infinity. I have the negative 1 coming in. I have a negative 1 to the n here, and then x to the n. So now this is the derivative with respect to x of, put these two together, right? So that's going to be summation n equals 0 to infinity of negative 1 to the n plus 1, and then x to the n, like that. So at this point, using what we learned about with differentiation of power series, I'm basically going to be using the power rule here. I'm going to treat this as a constant, and I'm going to bring out the n as a power and then reduce the power by 1. And then also remember, because we're differentiating, the index is going to shift from n equals 0 to n equals 1. So taking the derivative now, we get sum n equals 1 to infinity, a negative 1 to the n plus 1 times n x to the n minus 1. So let's see if that's what they want there. So, okay, so now we want to try and find the radius of convergence of this, right? Do they want to know that? That's part A. Find a power series. What's the radius of convergence? So how should we rewrite this? Well, there's a couple of ways. What I'm going to do now is try and get this to be an x to the n instead of x to the n minus 1. So what I want is for my n minus 1 to turn into just an n. So what I'm going to do is I'm going to replace n with n plus 1. So if I replace that n with n plus 1 minus 1, then this will turn into n. So everywhere in the problem, what I'm going to do is I'm going to replace n with n plus 1. So I'm going to rewrite this. Sum. That n right there is going to become n plus 1 equals 1 to infinity. Negative 1. Now I replace this n with n plus 1. N plus 1 plus 1. And then I have this n becomes n plus 1. And then this x to the n becomes x to the n plus 1 minus 1. Now, remember, the whole goal was to try and get our power series to have an x to the n and our index starting at 0, and this should do it. Let me write this above here. This is a tricky part of the problem. So, subtract 1 from both sides. Sum n equals 0 to infinity. All right, this is n plus 2, but it doesn't matter if I add 2, if I add 4, if I add 6. That's the same as negative 1 to the n, because when I plug in 0, I get an even number. When I plug in n is 1, I get odd, and the same thing would happen here. If n was 0, it's even. If n is 1, it's odd. So I'm just going to change that to this. If you don't like that explanation, then just rewrite that as this. So this is this, and negative 1 squared is just 1, so it won't matter. Then over here, n plus 1, and then x to the n, right there. So that's our power series. You can see, hopefully, that this part is our c sub n, and this is our x minus a to the n right there. So to find the radius of convergence, we need to do a ratio test on this. So I'm going to take the limit as n goes to infinity of, okay, we plug n plus 1 into this whole thing. So negative 1 to the n plus 1. And then if I plug n plus 1 in there, I get n plus 2. And then x to the n times x. That's this. Now divide that by, or sorry, that's this with n plus 1 plugged in. Then just plug in just n. And so I have n plus 1. Then x to the n. I need that to be less than 1. The x to the n's cancel. These don't matter. And so I'm getting limit n goes to infinity. Okay, in terms of n, I've got n plus 2. Here I've got n plus 1. And then an x, I need that to be less than 1. And if you take this limit, this is 1. So you get absolute value of x less than 1, which means our radius of convergence is 1, and our interval of convergence is negative 1, 1. I don't think they asked for the interval of convergence. Did they? No, they didn't, but all right, that's good. Now, it says, for part B of this problem, it says to find a power series for another function. It's this cubed instead. Well, we just found our power series, right? We just determined that if we have a function, let's call this something else. Let's call this g instead. We know that the function 1 over 1 plus x squared, which is the one we just worked out, was this power series, equals sum n equals 0 to infinity, negative 1 to the n times n plus 1 x to the n. That's what we know. So that's what we have so far. We want to know what the power series for this one is. So again, what I'm going to do is I'm going to somehow connect these two together using a derivative. So my question to you, or our question to ourselves, is how is this connected in terms of a derivative? So let me differentiate this and see if the derivative of this is that. So what is the derivative with respect to x of 1 over 1 plus x squared, like that? What's that derivative? Well, I can use chain rule. Let me bring the 1 plus x to negative 2, bring it up like that. So just bring it up. Now let me take derivative. Negative 2 comes out. So this equals negative 2 comes out. 1 plus x to the negative 3. So that came out. Take the power down. Take derivative of what's inside, which is just itself. So this is just equal to negative 2 over 1 plus x cubed, which is almost that, right? It's almost that. If I pull the negative 2 out, 1 plus x cubed. So how can I put all this together? Well, what I can say is that if I take the derivative of this, right? The derivative of this is equal to that. So if I take negative 1/2 times f of x, right? And take the derivative, right? So if I take derivative of this, I get that. Multiply it by negative 1/2, and I'll get this. So here's what I can do. I can say that this is equal to negative 1/2 times the derivative of the f function, which is negative 1/2 times the derivative with respect to x of the f function. What is the f function? The f function is this, written as a power series. There we go. All right, I hope that makes sense. All right. So now let me take the derivative of this power series. Again, this part is our c sub n. We're going to ignore it. We're just going to do the power rule. N is going to come out. We're going to subtract 1 from this. This index is going to go up by 1. So this is equal to negative 1/2 times summation n equals 1 to infinity, negative 1 to the n, n plus 1, and then the n came out times n. Power goes down by 1, and that's it. Okay, so this is a power series representation of this. Now again, what I'd like to do is try and get this to be an n and this to be a 0. So I'll do that same swap that we did earlier. I'm going to take all my n's and I'm going to replace them with n plus 1's. So let's rewrite this power series. This is negative 1/2 summation n equals 1 to infinity. Negative 1, I replace that with n plus 1. And then I replace n plus 1 here, so n plus 2. I replace n plus 1 there, so n plus 1. I replace n plus 1 there, I get n plus 1 minus 1 is x to the n. Oh, sorry, I forgot to replace. This was n plus 1 equals 1. So when you do this, subtract 1 on both sides, this is n is 0. All right, looking good, looking good. So now what I'd like to do is take that negative 1/2 and put it inside, and I'm going to split this negative 1 up right here using that power. So I've got sum n equals 0 to infinity, negative 1/2, negative 1, negative 1 to the n. So that's just splitting this into 2. Then these two, n plus 1, 2 times n plus 1, and then times x to the negative, or x to the n. And I'll put these two together, which will give me 1/2. Sum n equals 0 to infinity of 1/2. I still have a negative 1 to the n. And n plus 2, n plus 1, x to the n. What was this, 13b? All right. Then, part C, it says, now let's look at a different function. Different one, h of x is x squared over 1 plus x cubed. So it says find a power series for this one. Well, this is just the same as x squared times 1 over 1 plus x, that quantity cubed. But that's just x squared times this, sum n equals 0 to infinity, 1/2, negative 1 to the n, n plus 2, n plus 1, x to the n. So what I'll do is I'll put the x inside here next to this one. And when I do that, I get sum n equals 0 to infinity of, let's see, 1/2, negative 1 to the n, n plus 2, n plus 1, and then x to the n times x squared. But I'll put those two together and make it x to the n plus 2. And I believe that's all they want for that. Now, if you want to try, I mean, this is fine, but if you want to try and rewrite this so that this is x to the n instead of x to the n plus 2, you're going to have to replace your n's with n minus 2's. So if I put n minus 2 in here, this will be an x to the n. So what I'd like to do is replace all my n's with n minus 2's. So sum, I get n minus 2 equals 0 to infinity, 1/2, negative 1, replace that n with n minus 2. If I do n minus 2 plus 2 here, I get n. If I do n minus 2 plus 1, I get n minus 1. If I do n minus 2 plus 2, I get x to the n. And moving this, adding 2 to both sides on that one, adding 2 here and here, you get sum n equals 2 to infinity. And then here, remember that this really means negative 1 to the n times negative 1 to the negative 2. But this really means 1 over negative 1 squared. Negative 1 squared is 1. So we don't even need this piece. So that means I don't need to even account for that. So that should work. So that should be the power series representation of that last function. Make sure I've got all that 1/2 in there. Yep. Okay. And then you could do the ratio test and figure out, it doesn't ask for it, but you could do the ratio test and figure out the radius of convergence. All right, that's 13. All right, let's try 14. 14 is going to be similar to this, I think. Let's see. Use equation 1 to find a power series representation for, so 14. It gives you a function, natural log of, where's equation 1? What are they talking about? Natural log of 1 minus x. All right, so let's take a look at that. That definitely doesn't look like 1 over 1 minus u, which is what I need. But notice that if I actually take the derivative of that, I do get this, close to it. So what is the derivative of f? Well, it's 1 over 1 minus x, then times derivative of what's inside, which is negative 1, which is negative 1 over 1 minus x. So if the derivative of f is this, and this is something I can turn into a power series, then what I need to realize is that f of x, which is natural log of 1 minus x, is actually the integral of this. So So if I take the antiderivative of this, I should get this. Why? Because the derivative of that is this. So working backwards. So what I need to do is just try and figure out how to integrate this. I'm going to turn this into a power series now. So I'm going to write this as integral -1 times 1 over 1 minus x dx. And then here's the thing I can turn into a power series. So I have, let me pull the negative out of the integral. Negative integral, this is summation n equals 0 to infinity of just x to the n dx. So I want to integrate this power series. So when we integrate a power series, we use our general formula that I gave you in class. The big thing about integration is that you do not have to do anything with changing of the index. So realizing in here we have a 1, that's our c sub n, and we use power rule on x to the n. So negative, this equals negative, and then now the antiderivative of this, sum n equals 0, don't change the index, only do that when we're differentiating, and then 1 over n plus 1, x to the n plus 1. The c sub n I just left alone, it's just 1. And I've already done the derivative. Now I do also have to remember I have to add a constant of integration to this. And we're there. Now I'm going to move the negative back in here. I'm going to move it right there. And so I think at this point we can try and change the index over. Let's try and get this to be an x to the n. So I need an n minus 1 there, right? I need to change my n's to n minus 1s. And that will give me an x to the n there. So rewrite the whole thing. I'll do it in red because I'm changing the index. N, changing it to minus 1 to infinity. Negative 1 over, replace that n with n minus 1. So it's n minus 1 plus 1 is n. X to the n minus 1 plus 1 is n. And then, of course, I still have a constant. And then when you move this, add 1 to both sides, you get n is 1 here. So that would be the power series that represents the natural log of 1 minus x. Okay, negative, let me just make sure I've got everything going here. Yeah, that looks good. All right, so now on the next part of this problem, it says, find a power series representation for a different function. So I'll call this function, I'm going to leave the red one up there. Just remember that this right here equals the natural log of 1 minus x. That's the power series for that. That's what we just found out. So now they want to know for what is the power series representation of the function. I'm going to call it something other than f. I'm going to call it g of what's the power series representation of x natural log of 1 minus x. So all we need to do now is just tack an x onto this. So this will be an x times this series. So the x is going to go at the back. So sum n equals 1 to infinity of negative 1 over n, x to the n times x. But that x can join with this one, n plus 1. And now let's get this to be an n instead of n plus 1. So I'm going to replace n with n minus 1. And when I do that, I get, if I replace that with n minus 1 and add 1 to both sides, I get sum n equals 2 to infinity, negative 1 over, I'm replacing n with n minus 1, so that's n minus 1. X to the n minus 1 plus 1 is just n. So that would be your power series representation of G. Let's see here. They did that a little different. Why did they not? They didn't switch it. Okay. They just left it like this. That's okay, though. I mean, this is the same thing, just changing the index. And then, letting x be 1/2 gives natural log of 1/2 equals, I'm not going to do part C. I should go back to part A real quick, just to show you something I didn't show you. How we could find that constant of integration. Remember, we found that natural log of 1 minus x was equal to, where is it? We found that that was equal to negative sum n equals 1 to infinity of x to the n over n, and then plus some constant. Let's try and figure out what that constant is. So what I'm going to do is I'm just going to let x be 0. If x is 0, we get natural log of 1 equals negative sum, and then what happens here? If x is 0, this all goes away, plus a constant. And so if that's all 0, then I get natural log of 1 equals c, but natural log of 1 is 0, so c is 0. So in other words, our constant of integration is 0. So that would be the power series for this. Sorry, I forgot to do that. So we just picked a nice convenient point that we can figure out this side. Like we know that natural log of 1 is 0, so I picked x was 0. And it worked out real nice. We were able to get c. All right. Okay, let's look at number 15. Find a power series representation and determine the radius of convergence for f of x equals natural log of 5 minus x. All right, so let's take the derivative of that real quick. The derivative of this is 1 over 5 minus x times negative 1. And that's equal to negative 1 times 1 over, let's factor out a 5 on the bottom, 5 minus 1/5 x. Trying to make it look like 1 over 1 minus u. I'm working on it. And that's equal to negative 1/5 times 1 over 1 minus 1/5 x. So if the derivative of this is this, then the antiderivative of this is this. So I'm going to try and find the antiderivative of this. I'm going to convert this into a power series. So our original function, right, our original function should be equal to the antiderivative of negative 1/5 times 1 over 1 minus 1/5 x dx. Let's convert this part to a power series. So, and we'll take the negative 1/5 out. Negative 1/5 integral the power series n equals 0 to infinity of this. Here's u, so 1/5 x to the n dx. And then this is equal to negative 1/5 integral sum n equals 0 to infinity of 1/5 to the n times x to the n dx. So I'm about to integrate that power series in there. And I had to peel off to get my c sub n. Here's my x minus a to the n. And so all I have to do is use the power rule for antiderivatives. So I'm just going to go 1 over n plus 1 x to the n plus 1. I'm not going to touch that, and I'm still going to have a negative 1/5 out front. So here, I'm going to go back up to this. Negative 1/5 summation, no more integral because I'm about to integrate, Does not change the index, still stay at 0. And then I have 1/5 to the n, which doesn't change. I have 1 over n plus 1, x to the n plus 1, plus some constant. Now what I'd like to do is bring that negative 1/5 in. So I'm bringing that negative 1/5 in. I'm going to leave a negative 1 on the outside. I'm going to peel off the 1/5. I have a 1/5 to the n. I have 1 over n plus 1, x to the n plus 1, plus some constant. And then I'll put these two together, which will give me 1/5 to the n plus 1. And that is a power series representation. Now, my guess is that the book's probably going to want you to turn this into an x. Well, we're going to need to turn this x to the n so we can find the radius of convergence. So to turn this n plus 1 into an n, I'm going to have to replace all my n's with n minus 1. So let's see what happens when I do that. Replace all my n's with n minus 1s. So if I replace that with n minus 1 and then add 1 to both sides, I'm going to start at 1, and then negative 1 just sitting here. If I replace this n with n minus 1, I'm going to get n minus 1 plus 1, that's just 1/5 to the n. If I replace this n with n minus 1, I get n minus 1 plus 1, that's just 1 over n. And then over here, x to the n. And then of course, I have a plus a constant. That's it. So that's a power series representation of this. Which one am I doing here? 15. Okay, so let's try and figure out what our C is. Okay, we can do that real quick. Remember, this is what the natural log of 5 minus x is. So let me let x be 0 again. If x is 0, now the reason I'm doing that is because if I let x be 0, this whole thing is 0. So if x is 0, we get natural log 5 equals 0 plus c, which means that c is natural log 5. All right, so I know that c is natural log 5. All right. Now, radius of convergence. So I'm going to take the limit, then goes to infinity. I'm going to use the ratio test on this. So I get negative 1, then 1/5 to the n times 1/5 times 1 over n plus 1 times x to the n times x. So that's just replacing all my n's with n plus 1s. And I'm going to divide that by, replace everything, or just leave everything as n. So 1/5 to the n, 1 over n, x to the n. I need that to be less than 1. These will cancel. These are canceled. These don't matter. And we have a fraction over a fraction, so I can flip. And so I'll get something like limit n goes to infinity, n over, now the 5 is still on the bottom here, so I'm going to go 5n plus 5, distributing that 5 through. And then I still had an x over here, less than 1. If I do L'Hopital on that, I'm going to get 1/5. So I have absolute value of 1/5 x less than 1. And then work this out. We've done this several times. You get that. So radius of convergence is 5 because of that right there. Now it doesn't ask for an interval, so I don't need to check endpoints.